All right, so this should flow pretty nicely. I think you guys got that last section there. So now we're going to look at exponential modeling of this, right? So it's going to be a lot like what we just did, only it's going to be happening repeated times, and so that's handled by putting an exponent or a variable up in the exponent, right? So here's an example. Population of fruit flies growing at a constant rate. What percent? 6%. How often? Every hour, right? What's the starting population of flies? So at t, 0 hour, time of 0, we have a starting population, 28 flies, okay? So let's go ahead here and see how many flies we'll have in part A, right? Usually we learn in the last lesson, okay? So in 1 hour, right, population P equals, what's the starting amount? 28 times 1, and it's increasing, so 1 plus what? 0.06, right? Which is 1.06. How many flies do we have? Yeah, well, how about 29 flies? Really? Yeah, well,
No, but like in a live fly.
yeah, I mean, really that would be rounded up to, 30, but since it's actual whole units of flies.
Yeah, but you can take their wings off the
You
floor.
could, yes, that's true, right. However, that's not part of the story. So anyway, after 2 hours, what's our new starting amount? 29 flies times 1.06 again, right? And what do you get? Just approximately what? Front of the nearest whole fly. 30 flies, okay. And now for the third hour, now we got a new starting amount, 30 times itself and 6% of itself again. I don't know, is it? Oh, this is 31, isn't it, up here?
No.
This would be 31.
Why?
Well, all right. No, that's 30. It's 30, I'm sorry. So what's this going to be?
31. So it's just going in by 1.
31, right? Now, it might work a little different when we get the exponential part in there, because when we do that, we're not... Let's do it. You know what? Let's just simplify this. I'm going to simplify this. Let's go ahead and call that 30. Close enough for government work. And if that's 30, then that changes a little bit, and then that changes, right? Let's just keep that as 30 as I think about it now. So this would be 30, and then what do we have here?
31.
Now there's 31, and now 31. 33, isn't it?
No, it's 33.
Comes to 33. We're going to round up the next fly just to some. Okay? But really, let's do a formula here. What's the starting amount?
28.
So population P of T, right? Population is a function of time in hours, right? Is going to equal, what's our starting amount, A? 28. What is the growth factor? 0.06 to the what power? T every hour.
I think 31 is 32. The T power.
It's okay. It's not super important right now. All right, so this is our y equals AB to the x, right? You notice that the b here, this is greater than 1, so it's growth, right?
Yeah.
Okay?
Is that 33?
33.
30, 31, 33.
So
All right. So part C, value P of 24. We know how to do this, right? 28 times 1.06 times 24. So what's that give you, kids? Push buttons. So about 113 flies. You guys know the approximately equal to sign, right? So So we'll call that 113 flies after 24 hours. Okay?
I think our calculator is actually broken. No, it really is just really.
Maybe. All right, part D. What does the calculation you made in C, all right, 24 hours, 113 flies, represent about the fly population? From 0 to 24 hours. Is this time from 0 hours to 24 hours? How long is that actually? So 24 hours equals 1 day, right? So what could we say about this? Population at the end of what?
Population at the end of 1 day is 113 flies.
That's what we can say then, right? The population at the end of 1 day is 113 flies. Okay? So this is our domain, 0 to 24, right? The inputs, 0 hour to 24. What's the...
domain?
All the input values that are possible. The x's and range is the y's, remember? So now I want to find the range. So what is the range in between? Range is the output of our function. What's the lowest value of our function? It's started with 28 flies. And at 24 hours, what was the highest value? Okay. So we can say that 28 is less than or equal to, was it P, the population of flies? And then in between, 113. Right? So if this is my domain, then this is the range of outputs that go with those domain of inputs. Remember doing that, yeah? Domain is inputs X, well, T in this case. Range is output Y's, or P in this case. All right? All right. Well, they want us to use a calculator to sketch this from 0 to 24. Right? So why don't we all grab a graphing calculator real quick. So this is going to be your X values from 0 to 24, and this will be your Y values. So we have to open up the graph, like the home. Remember, you hit this thing once, maybe twice if you have to, right? I'm going to change the window, menu, window zoom, settings. So X, that's our T, 0 to 24, right? And then a Y, or P in our case, 0, what did they say, 120? A little bit above. I'd almost rather go out maybe 25, whatever. So notice all like first quadrant, right? Real life situation. So I hit your tab button. And it was 28 parentheses. What was it, 1.08? 1.06. 0.06. Caret button for the X. Well, yeah, but then if we kept on going here, remember this will start to tail up very quickly at some point.
It won't be going straight up because it's...
Correct. And by the way, it doesn't have quite the super increase that we're used to, because we're just a little bit over 1 for the B, right? We're only 6% over. It's not like we have a B of 2 or 3, right? Doubling or anything every hour, right? So what's the y-intercept here? Or you could look at the function. You could do it there, right? Starting amount is that, yeah? So let's sketch that. So if this is our function up here, our starting amount is what? 28. That's the y-intercept, right? So what kind of interval? So So this is up here at 120, and this is out here at 24, like that. 28 would be, I don't know, right about here. And doesn't it kind of do something like that? Up to 20, so we only stopped at 24. It's 113, right? Okay. Remember, like if you get this graph on your calculator, ooh, what's the y-intercept? Well, your calculator can figure it out for you, or you can just look, there's my y-intercept. Remember, that's the starting amount for 28. Okay? We okay with this? Let's look at exercise 2. For savings. The savings in a bank account can be modeled by the function S of t. Savings is a function of time equals 250 times 1.045 to the t. Okay, t is time, right? So look at your choices here. And now look at the function they gave you. Looking at that function, can you tell the starting amount of money in the savings? $250, right? So this is the initial amount deposited was $250, right? What's the rate though? What's the interest rate? Is it 1.045? No, it's 1 plus something, isn't it? So wasn't this, remember when we set this up, this was 1 plus 0.045?
Yeah.
Right? Okay. So in other words, it was, so 1 plus R equals 1.045. See what I did there? And if I subtract 1 from both sides, what's the R equal? 0.045. Right, I just kind of did algebraically the way Letty did it in your head there, right?
So it's 45%?
Yeah, right?
So it's
No, it's not. What? How many percent? 45? I'm coming to you. When you grow up
4.5.
and you're a bank manager, Tegan, I am putting all my money in your bank. 45% interest on my money?
I don't know what that is.
You're getting a lot of money back.
What's the actual interest rate? 4.5%. So what's our answer? Choice 3. 45%. I'm putting every penny I have in your bank.
I don't know.
Tegan Allen Trust and Savings Account.
I don't know what that
Savings
means.
Bank.
If
40.
you're poor, you get a lot.
All right. Next page. Probably guess we might go the other way, right? Get some percent decay. So instead of 1 plus, we might be looking at what? 1 minus, or what, like if they tell us it goes down by a certain percent, we need to think of what percent remains, right? Like if something goes down 5%, what percent remains?
95.
Okay. If something is cut in half, what remains? Half or 50%, right? Okay. So, exercise 3, you got water draining out of the pool. And what rate does it decrease, everybody? 20%, right? So it decreases at 20%. Okay? What remains, by the way, if it decreases at 20%?
80.
So 80% remains every, what, hour, right? So basically, it's our 1 minus 0.2. What's 80 as a decimal? 80%. 0.8. What's 1 minus 0.2? 0.8. You see, same thing? Okay. What's the starting amount of water?
12 feet.
Wouldn't that be like our A in the thing? All right, so the depth after 1 hour, so we can do this quickly, right? There would be 12 times what number? No, 1 minus 0.2. What remains?
80. 0.8.
0.8 after 1 hour. So wouldn't that be to the first, right? One time? What's that give you? So 9.6 feet, right? Let's go to hour 2. So 12 times 0.8% again. Well, I'm doing it a little differently. See what I did that was differently?
You squared it.
Square.
Instead of starting with that, right? What's that give you? $7.7 feet, right? Now, after the third hour, it'd be 12 times 0.8 to the what? 3. So instead of like, yeah, using a new starting amount, you should get 6.1 feet after 3 hours. Okay? So that looks like exponential decay, right? You notice that b, that 0.8, is between 0 and 1? So let's write our function. Depth of the pool as a function of t, time, and hours, right, equals, what was our starting amount? Y-intercept? 12 times 1, well, 1 minus 0.2 to the t, right, but just want to show you that. 12 times 0.8 to the t. Right? You know where the 0.8 comes from. You what? Yes, Anna? I thought you said something. Okay, so every hour t, 80% of the water depth remains. Okay? All right. Well, maybe that'll come to you as we go along. Let's graph it then. So we have a new window. There's our function. So the t's are the x's from 0 to 20, and the d are the y's from 0 to 15. So let's all put that in our calculator. We can clear out this other one. So I'll do menu, action, 1, delete all, 4, yes. Let's change my window, menu, 4, let's see, 0 to 20. Yep, right, 0 to 15. Okay. Now let's put our thingy in there.
I find that the well thing,
Is the what?
the relation.
Well, now go back and do it this way. Just
I forgot how to go to that one.
push the menu, graph edit entry function. Got it? 12 times 0.8 parentheses exponent x. Get that?
Something wrong.
Oh, it's decreasing. Like I guess like the.
Oh, you're way matrix.
It's not me because I want to turn it on.
You can put your function in, but you gotta change your window. All right. So there's your graph. Notice how it decays more and more quickly, right? Or more and more, actually slowly, it slows down its decay. It's, right? Because water has weight to it, right? Like the more water in, the more pressure it is pushing to get it out the bottom, right? Okay. What's that y-intercept there? Can we find out? Can you use your calculator? Oh, it's 12. It's right in our function, right? So let's go in here and just sketch the graph real quick. So I'll do 2, 4, 6, 8, 10, 12. Put the caret button and then X. And that's 0 to 20. 0, we'll go out here to 20, close enough, right? So it starts at 12. Kind of goes down like this, and we're going to stop at 20, right? We're not going to put an arrow on because it said to just stop there. Okay? Let's look at the follow-up question real quick. Safe to cover the pool when it reaches a depth of 1 foot or less. Okay? Water. How many hours? So we need to kind of figure that out, right? So an estimate, yeah, I think it's that many hours. Let's do like a table. So time in hours, depth. So remember, your calculator will do a table, right? Yeah, you know what? Huh?
Control T.
That or menu, right? So if I hit menu, 7 is table, right? So there's a table of values, right? This is kind of what we calculated, wasn't it? First 3 hours. We want to be less than a foot. That's still more than a foot. It's more, right? We'll just go down and get those in there. So at 11 hours is 1.03, right? 11, we got 1.03 feet. What was it at 12?
8.24.
8.8.
0.84. So we're under a foot here, right?
It doesn't matter, honestly.
How about just 0.8? Right, because we just want to be, you're right, Tegan. We just want to be under a foot, right? So 0.8 feet. So when's it safe?
12.
Yeah. So after 12 hours. Later math classes, you'll learn how to solve for an exponent, right, with logarithms, but we're not going to do that here.
Isn't it,
This is, it did a table. It's clear. Yeah, right, see, there it is. Got it? All right. What about exercise 4? Which one of these would model exponential quantity that begins with a level of starting amount of 16 and decreases at 8% per hour? What do you think?
Minus or 0.9.
It'd be like y equals some a times 1 minus r to the t,
Number 1.
right? Okay. Well, let's just fill it in. Let's just write it. Y equals, what's the a in this case? 16 times 1 minus what? 0.08 to the t. And what is 1 minus 0.08, kids? 0.92 to the t. So now we don't have to guess, right? You're going to write that now, don't you?
It's number 1.
Number 1. You're number 1.
Yay! I'm number 1.
wait, do you get, 0.92 from,
1 minus 0.08. Yeah. All right, last one. 350, placed in the savings, 3.5% once a year. How much would be after 10 years? So what you want to do is write a function for this, okay? Savings, we'll do S of t equals, write your function as a function of time. Everybody, you do it on your own. And then you'll plug in 10 for your t once you get it written, okay? What's the actual function? 350 times 1 plus what? To the t, which is actually 350 times 1.035 to the t. Yeah? You get that function? Now just plug in what for t?
That's 493.71.
Yep, $493.71. And there you go. Okay? Yep. We'll handle the Regis questions tomorrow.